I'm Peiming. In this video, I will introduce our work DCC, Data-Centric Compilation of Machine Learning Kernels for Processing Memory Architecture. First, let me give a short summary. For PIM system, the host processor and PIM cores require different layout, causing expensive data rearrangement. Current PIM compilation approach largely ignore this and only design for single backend or few kernels. Therefore, we propose DCC, the first data-centric machine learning compiler for PIM system that jointly optimize data rearrangement and compute for multiple PIM backends. DCC has 5 key components. Multi-layer PIM abstraction enables support for multiple PIM backends. Data-centric schedule generator co-optimize data and compute loop partition. PIM-specific code optimizer perform PIM-specific performance optimizations. Coupled predictor select the best configuration across joint compute loop and data partition. Intermediate representation is a data-centric IR that can be lowered to multiple PIM backends. DCC shows significant performance improvement for both machine learning kernels and end-to-end large language model inference using various PIM systems. Let's start with some background. Currently, critical large language model kernels are bottlenecked by data movement. This roofline plot confirms this trait. The orange attention dots are fully bounded by the memory, and the blue fully connected layer are also bounded by the memory when the batch size is small. Processing in memory solving this by embedding the compute unit right beside the memory bank. And many prior work adapts the nearbank PIM system to accelerate machine learning workloads. Nearbank PIM systems usually have two major parts. One is the high-performance processor, host XPU, like GPU or TPU, and the host memory space. The other part includes multiple PIM-enabled memory devices. Each device contains many low-power processing unit PIM core close to one or few memory banks. Such design provides immense aggregate memory bandwidth and high-level execution parallelism. But host XPU and PIM cores requires different data layout. Hosts spread consecutive data across different memory banks. Instead, PIM core require all consecutive data must stay within one PIM bank, because PIM core can only access the data inside their local bank. This data layout difference results in explicit software rearrangement to run a machine learning kernel on the PIM core, resulting in these 3 steps. First, rearrange input data to fit the PIM local bank data layout. Then, execute the compute on the PIM core. And finally, rearrange the output data to combine the partial results and restore the host accessible data layout. However, existing PIM compiler have 2 major limitations for such machine learning kernel execution pipeline. First, existing compiler either only support a single PIM backend or only optimize for single machine learning kernels. And secondly, existing compiler follow a compute-centric approach, largely ignore the data rearrangement cost during the compute loop optimization step. A compute-centric compiler following these steps. First, it generates a fixed set of optimized compute loop partition scheme for the step 2, kernel execution. Then it generates the corresponding data partition strategy for the fixed optimized set of compute loop partition strategy. Finally, it selects the best performing configuration among these fixed set of compute loop and data partition strategies. We found that the compute-centric approach is not optimal because the data rearrangement time is a significant part and can't be discarded. We compare the compute-centric compiler using TVM compiler versus a manually tuned best-performing implementation. The result shows the manually tuned one with slightly worse compute time could achieve better data rearrangement time and resulting much better end-to-end kernel performance. This shows that data rearrangement and compute code optimization are interdependent. They must be jointly optimized during the compilation. A less efficient compute transformation could enable a cheaper data rearrangement. We need a compiler that's generating and optimizes the combination of compute loop and data partition strategy for all 3 steps. Then select the best performing configuration from these combinations. To solve these two limitations, we designed DCC, which is the first data-centric machine learning compiler for Peim system that jointly co-optimized compute loop and data partition strategy into a unified tuning process. DCC includes 5 key components: multi-layer abstraction, data-centric schedule generator, Peim-specific code optimizer, coupled predictor, and the intermediate representation. And it has low compilation time and consistently deliver near optimal performance for multiple Peim backend and any machine learning tensor kernels. DCC's first component is the multi-layer abstraction that enables support for multiple current and future Peim backends. We map Peim memory hierarchy into a compute hierarchy over 3 levels. First, the system level covers the host XPU, host memory space, and the multiple Peim devices. Second, the Peim group level includes multiple Peim groups or many Peim cores in the same memory channel or rack. Third, the Peim core level focuses on individual processing units paired with their own local memory banks. This Peim abstraction can be mapped into multiple existing Peim systems, including the HBM Peim from Samsung, the Tech Peim, and the AIM Peim from SK Hynix. DCC's second component is the data-centric schedule generator that generates the candidate combination of data partition and compute loop partition for each Peim core. These candidate combinations are represented as the candidate tiling drafts. It has 4 steps to generate the candidate tiling drafts at core level granularity. The first challenge we need to solve is how to associate data partition with the compute loop partition. In other words, if we have a partition of the tensor dimensions, how should we map them to the compute loop partition? DCC uses dimension set to solve this problem. Each dimension set includes mapping functions that associate tensor dimensions with the loop variable. For example, with the loop variable I, here are 2 tensor indices of the dimension A0. So the first dimension set includes 2 mapping functions corresponding to the indices of A0. Similarly, we associate all tensor dimensions with related loop variable using the corresponding mapping functions. Then, DCC performs an exhaustive search to generate all data partitions for each dimension set. To decide the dimension to partition, DCC selects a mapping function in each dimension set as a representative one. For the first dimension set, here are 2 candidate representative mapping functions, and for the second and third dimension set, we have 3 and 1 choices. Then, DCC searches for all possible allocations of Peim groups and cores per group for each dimension set. For example, if we have 2 Peim groups and 4 cores per group, there are 2 times 4, in total 8 different candidate configurations on how many Peim groups and Peim cores per group can be used for this dimension set. Then, the search result of these 2 steps will be combined. With these 2 search steps, DCC creates many candidate data tail drafts. For example, this draft has 3 parts, 1 for each dimension set. Each part has 3 entries: the number of Peim groups, the number of Peim cores per group, and the representative mapping function. Similarly, these drafts include the corresponding part for the other 2 remaining dimension sets, and in total in this example, we get more than 3,000 data tail drafts. To make the compilation fast, we apply 3 hardware-aware pruning routes to remove the data tail drafts that have very poor performance, like the drafts that cause extreme data rearrangement costs. Our effective pruning eliminates roughly 90% of all raw data tail drafts, remaining only the top 10% of promising ones. The next step is to generate the compute loop and data partition at the Peim core level. With 1 data tail drafts and the tensor dimensions, we get the dimension length and the number of tails for each dimension set. By calculating the tail size for each core, DCC mapping the high-level resource allocation to the core-level loop partition and data partition for all dimension sets. These core-level candidate tailing drafts are represented by the DCC's representation and feed to the third components, the Peim-specific code optimizer, producing optimization strategy associated with each draft. DCC enables many PIM-specific optimization to further improve the performance. For example, in a naive execution when we have 4 PIM cores per group that we need to do a make operation, the host sends 4 make commands to the 4 cores in a PIM group. But DCC enables group-level broadcast command when the backend is supported. These 4 commands are replaced with single broadcast command at the group level that reaches all cores in the same group. This is an example of the PIM-specific optimization. This optimizer of DCC can be easily extended to support additional performance optimization. To quickly and accurately estimate and select the best performing drafts among the candidate optimized drafts, DCC uses a coupled predictor. It uses a trained XGBoost-based predictor. It takes both the optimized tiling drafts and the specific PIM backend information as inputs. Then our predictor estimates the end-to-end execution time for each candidate draft, and selects the one with the faster runtime as our final best configuration. Lastly, our data-centric IR can capture optimized data partition strategy and compute loop partition schemes, and lower them to multiple PIM backend. The best performing configuration token from the coupled predictor is translated to our data-centric DCC IR. The IR contains the core level tiling information and the compute code. For different PIM backend, the IR will be transformed to different PIM backend instruction. For example, this line can be lowered to attack PIM instruction or HBM PIM instruction as shown in these two boxes. At the same time, programmer can easily write PIM kernel with our Python interface. The kernel is described by the Python loop list, and with the necessary DCC initialization, this PIM kernel can replace any layer in a machine learning model written with PyTorch. With the data-centric design, DCC shows significant improvement in the evaluation. We evaluate DCC on a modified version of a text simulator, which is based on Remulator 2.0, and it simulated NVIDIA A100 GPU with 5 PIM-enabled HBM3 devices. We have tested on 2 PIM backend with 5 individual machine learning kernel and 3 large language models. We have 5 comparison points: the GPU-only execution, the attack and HBM PIM backends using the default kernel implementation with fixed data partitioning, and the attack and HBM PIM backend with our DCC compilation enabled. This plot shows the machine learning kernel performance running on the attack backend, normalized to the baseline implementation that runs the kernel on the GPU. DCC improves the performance by up to 1.7 times and on average 1.3 times over the default fixed implementation. Similarly, DCC provides significant speed up on HBM PIM backend, improving performance by up to 2.1 times and on average 1.7 times over default fixed implementation. We also ran the end-to-end evaluation of large language model inference on attack backend. Here are 2 versions of attack PIM backend. Attack base only runs the attention on the PIM core, and attack 4 runs both attention and a part of feed-forward layer on the PIM side. Comparing with attack's default implementation, DCC accelerates large language model inference by up to 2.7 times and on average 2.0 times. We also showed the DCC's performance improvement translated to also energy consumption improvements in large language model inference by up to 1.5 times over GPU-only running execution. We have many more results in our paper, including large-scale evaluation, pruning efficiency, and compilation time analysis. And DCC is open-sourced on GitHub. To sum up, DCC is the first data-centric machine learning compiler for PIM system that jointly co-optimizes data rearrangement and compute code in a unified tuning process. DCC supports any machine learning tensor kernels and multiple PIM backends with multi-layer abstraction and data-centric IR. DCC enables high performance via PIM-specific optimization, uncoupled compute loop and data partition co-optimization implementation. and DCC is fast and accurate on consistently finding the near-optimal configuration. DCC showed significant performance improvement for both machine learning kernels and end-to-end large language model inference using various PIM systems and have received all three artifact badges. Our source code and the extended paper is available with the QR code on the right side. Thanks for your listening.